Hello and welcome to the online CPD presentation on weathering steel bridges. My name's Chris Dolling and I'm the Manager of Technical Development at the British Constructional Steelwork Association. Over the next hour or so I'll introduce the subject of weathering steel. I'll describe the benefits of the material for bridge clients. I'll also talk about the limitations where you can't use weathering steel. I'll comment on the availability and the appearance before addressing a range of issues. I'll talk about design, detailing, fabrication and installation, inspection and maintenance, and finally possible remedial measures should corrosion rates exceed those anticipated at the design stage. So, weathering steel, what is it? Well, it's a high-strength, low-alloy structural steel that was first developed by United States Steel in the 1930s to resist corrosion and abrasion in their iron ore wagons. They gave it the trade name Core 10, and it was first used in construction in 1964 on the John Deere World Headquarters building in Moline, Illinois. It made it across the Atlantic in 1967 and was first used at York University on a footbridge that you can see in the slide, and it's still performing well today. It's widely available in Europe as structural steel with improved atmospheric corrosion resistance. It's a non-proprietary product and it's specified to BS EN 10025 Part 5. There are three grades available for bridge works. There's S355J0W, J2W and K2W. The standard also covers another grade which is S235, but this is rare and to my knowledge Tata Steel have never actually cast that material. One point to note is that there's no standard NL grade, which may be significant if you have particularly thick plates, say over 70mm or so. But the key feature with weathering steel is that you don't have to paint it. So how can that be? Surely it will rust. Well, yes it will. Weathering steel does rust. In fact, all low alloy steels have a tendency to rust in the presence of oxygen, moisture and contaminants. What happens is that the oxygen and the moisture attack the steel surface and create rust. Now this rust actually forms a barrier that slows down the access of oxygen and moisture to the steel surface. With ordinary steel, the rust layer falls off after a while, exposing fresh steel to the corrosion process. So for ordinary steel, corrosion progresses as a series of cycles, and that can be approximated to a straight line, and the slope of the straight line depends on the aggressiveness of the environment. With weathering steel, the key alloying elements in the material actually change the chemistry of the rust layer, so it sticks, it's adherent to the base metal, and it's less porous. So rusting initiates in the same way as ordinary steel, but because the rust doesn't fall off, it doesn't expose fresh steel to the corrosion cycle. So over time, as the material gets wet and then dry and then wet and then dry through a series of cycles, this rust layer forms a barrier that slows down the access of oxygen and moisture to the steel surface. So whilst weathering steel does corrode, it corrodes at a much lower level. So what are the benefits for clients and bridge owners? Well, clearly because you don't have to paint the material, you don't have to repaint the material. So it's a very low maintenance solution, which is particularly ideal where access is difficult or dangerous, such as over major roads or railways where you want to minimise future traffic disruption. It also gives you a low-cost solution. Whilst the material itself is slightly more expensive than ordinary structural steel, and also there are additional costs for the bolts and the fabrication, if you add all those up together, it comes to less than what you'd save from eliminating the paint system. So overall, weathering steel is about 5% cheaper than ordinary structural steel in terms of fabricated and erected steelwork. This was demonstrated by a comparative study of 8 UK bridges that was published by ECCS in their publication number 81. And you can see the results in the table. So 5% difference, not a great deal you might think. But when you start to think about whole life costing, there are huge savings for weathering steel, because not only are you eliminating the direct costs of the maintenance, you're also eliminating the indirect costs of the traffic delays. Speed of construction is another benefit with weathering steel, because both factory and site painting operations are eliminated, so it's faster. Weathering steel also gives you an attractive appearance that blends pleasingly with rural environments and actually improves with age. This example is Hayden Bridge Bypass over the River Tyne South, and you can see it's quite a nice setting with two fly fishermen in the foreground. Weathering steel also reduces the environmental impact of your project Because you're not painting the material, you don't have to worry about VOC emissions from the paint coatings themselves, nor do you have to worry about blast cleaning debris from future maintenance work. Health and safety is always important, and particularly so with bridge construction, so weathering steel ticks that box as well. Because you don't have to paint the bridge or repaint the bridge, you're eliminating the risks associated with initial and future painting. Now this is particularly relevant for box girders, because a box girder on the inside is a confined space. So by not painting the inside of the box girder, either initially or in the future, you're making huge benefits in terms of health and safety. Weathering steel also has a good track record in the UK. TRL carried out a study at the late 90s, early 2000 on the performance of all UK weathering steel bridges. What they found was that it's generally performing very well, with 85% no defects. Where they did find problems, it was the specific faults on a few occasions, typically leaking expansion joints. However, if you notice on the slide the green area, 5% of cases were due to general corrosion, and this was almost always due to the use of weathering steel in the wrong environment. So I'm now going to turn to the limitations of the material. Weathering steel can be used in most bridge locations, but there are one or two environments where it won't work satisfactorily, and in these situations it needs to be avoided. The first one of those is marine environments. Exposure to high concentration of airborne chloride ions is detrimental to the material. A build-up of salt deposits on the girders adversely affects the formation of the stable rust layer, and this is particularly a problem where you have seawater spray and coastal fogs. So general guidance in the UK is that you should not use weathering steel within 2 kilometres of coastal waters. The use of de-icing salt on roads both over and under weathering steel bridges can give you similar problems to marine environments, but only in extreme cases. The first case is where you have salt-laden runoff from a leaking expansion joint flowing continuously over the steel. This leads to a high build-up of salt deposits on the girders, and again the stable rust layer cannot form, and corrosion rates similar to those of ordinary structural steel must be anticipated. The second area where de-icing salt can be a problem is where you have a tunnel-like condition. This may be experienced at urban or suburban interchanges, where you have a narrow, depressed roadway between vertical retaining walls going under a very wide bridge with minimum headroom. Because you're effectively forming a tunnel, it's very difficult to get the airflow around the steelwork to dissipate the spray, and so you get a high build-up of salt deposits again. But de-icing salt is not a problem for typical bridges, such as the one shown on this slide, where the minimum headroom is 5.3 metres. This last point is worth dwelling on, because in the past there was a minimum headroom limit of 7.5 metres for weathering steel bridges over roads. That was due to concerns about the build-up of salt deposits from spray. However, part of the TRL study that I mentioned earlier also found that whilst bridges over traffic roads had corrosion rates that were higher than bridges over, say, rivers or floodplains, they were still sufficiently low that you could have a 120-year design life with a sensible corrosion allowance. So, in 2001, the Highways Agency published their document BD 701, and this removed the 7.5 metre headroom restriction. So now, weathering steel can be used at conventional minimum standard headrooms of 5.3 metres. Another area where weathering steel won't perform very well is in permanently wet or damp conditions. As I mentioned earlier, for the stable rust layer to form, the weathering steel needs to get wet and then dry. Now this wet and dry cycling is needed for the rust layer to form. Where it doesn't happen and it's permanently wet, then the stable rust layer doesn't form and you get high corrosion rates as you would with ordinary structural steel. So you should avoid using weathering steel where it's submerged in water or buried in soil or covered in vegetation. There is also a risk where you have a bridge over water that you experience damp conditions under the bridge. Now this is only if the bridge is very low to the water with a low clearance, or it's very wide so you don't get the airflow underneath the bridge. So there is a rule in BD 701 that the minimum clearance over the mean water level should be 2.5 metres, and this is purely to avoid the risk of damp conditions. The last area I'd like to look at in terms of limitations is where you have very high levels of atmospheric pollution. specifically high concentrations of sulfur dioxide. In these sorts of environments, weathering steel will not perform particularly well, and so the use of the material should be avoided. However, fortunately, such environments are rarely encountered in the UK these days. So that was limitations. I'd now like to turn my attention to the availability of weathering steel. And firstly, we'll look at plates. These are readily available direct from the UK mills from Tata Steel, and there's a minimum order quantity of 5 tonnes per width and thickness. Tata Steel supply all 3 grades for bridge works, so that's S355J0W, J2W and K2W, to BSEN 10025 Part 5. The limitations are presented in the table that you can see on the slide. The maximum plate width is 3.75 metres, the maximum plate length is either 17 or 18.3 metres depending on the process route. The maximum plate thickness is 100 mm and the maximum plate weight is 14.5 tonnes. Now the last row in the table is CEV, which is carbon equivalent value. This is effectively a measure of the alloy content in the material. The higher the number, the slightly more difficult it is to weld. So Tata Steel developed a low CEV version of weathering steel that you can see on the right, and that's produced through the normalised rolled process route up to 65 mm. It can also be produced through the normalised route up to 85 mm thick. So that was plates. In terms of weathering steel sections, rolled sections are not available in the UK or in Europe in weathering grade material. Now this is not a problem for the main girders of a bridge that you can see on the slide, because those are generally fabricated from plate anyway. But it is an issue for the angles and channels that are typically used for X or K bracing. So what should a designer do about the bracing on such a composite bridge? Well, there are several options. You could use temporary bracing using ordinary steel angles and channels that are then removed once the slab is cast. But that's not a particularly good solution, because once the slab is cast, there's very limited access for lifting equipment to remove that bracing. It also adds time and cost and has health and safety implications, so that is not recommended. Alternatively, you could use plan bracing within the depth of the slab. So this effectively forms a horizontal truss between the top flanges of 2 parallel girders. But again, that is not ideal because it tends to increase the thickness of the slab and also gets in the way of placing the precast permanent formwork and also the reinforcement. So what should you do? The advice on bracing in the UK depends on the type of bridge deck. So let's look at ladder decks first. The cross girders every 3 to 4 metres stabilise the top compression flange in midspan regions, so the only place to look at is the bottom flange adjacent to intermediate supports where it's in compression. On some composite bridges you'll find the use of angles to form knee bracing in such locations. However, with weathering steel it's advisable not to do this due to the availability problems of the angles. It's much better to go for a deep transverse girder, and this was the economic solution on the A34 M4 Junction 13 project at Chieveley that you can see in the slide here. This was designed by Mott MacDonald, fabricated by Maybe Bridge for main contractor Costain. For multi-girder decks, the advice is to avoid X or K bracing and use fabricated I girders spanning transversely between web stiffeners to form stiff H-frames. Again, this was the economic solution on the Chieveley project. Now that's fine if the girders are relatively shallow. Once the girders get to be quite deep, the compression flange is often quite a long way from the cross girder that is stabilising it. In such situations you may be forced to use X or K bracing. Now this can be achieved because you can fabricate angles and channels out of plate. There is a cost premium and it's advisable to talk to a steelwork contractor early in the project to discuss the bracing strategy with them. They have a wealth of experience and would be pleased to talk to you. The other essential element of bridges is bolts, and these have to be preloaded bolts and they have to be in weathering grade. Now there's limited availability of weathering grade bolts in the UK. Typically only M24s are available from UK suppliers. Consequently, many bolts are imported and most of these come from North America, so they come in imperial sizes and to US specifications. So once again, the industry advice is to standardise your designs on M24 bolts, but set your bolt groups out assuming you had 1-inch bolts, i.e. you have slightly larger bolt spacings. This gives the fabricator the maximum flexibility in terms of selecting his bolts. Once again, talk to the fabricator early in the project. If you know that the fabricator is going to be using 1-inch bolts, then you can take advantage of the slightly higher capacity in your designs, and also be flexible to accommodate what the fabricator suggests. So, moving on to the appearance of weathering steel. Initially, the material goes an orangey brown colour that you'd associate with rust, which many people think is unsightly. But during the construction period, and over 2 to 5 years, the colour darkens and it goes a characteristic dark brown. And this gives it a very natural appearance that blends well in rural environments. Now, the time it takes to go this dark brown colour and how dark a brown colour it goes depends on the nature of the environment. In industrial atmospheres, the change in colour will be quicker and the final colour will be darker than in rural atmospheres. On the subject of aesthetics, rust is definitely in at the moment. This example is called Pont Trencat, or Broken Bridge, in Catalonia in Spain. The original 2-span masonry arch bridge was built in around 1453 and was destroyed by the Spanish in 1811 to obstruct the advance of Napoleon's army. Napoleon still crossed the river on a pontoon bridge and defeated the Spanish, so it didn't work. But anyway, back to the bridge. The town council thought for a while about how to repair the bridge, and they thought for quite a long while, and all the while they were thinking about it, they grew accustomed with the appearance of their broken bridge, and it became quite familiar. When they eventually got round to commissioning a repair, one of the key criteria was that the new bridge had to retain the character of their old broken bridge. And I think this solution is a wonderful answer to the brief. Weathering steel moved into the field of art in 1998 when Anthony Gormley erected his Angel of the North in Gateshead, and it's now a material of choice with many sculptors. One notable example is the Millbank Steps, which was an exhibit in the Tate Britain in spring 2005 by Sir Anthony Carrow, and this was a 100-ton sculpture fabricated by William Hare. In fact, weathering steel is being used for all sorts of architectural statements around the world. The one on the left is a bandstand at the Crystal Palace, and the one on the right is an angel in Mallorca with stainless steel wings. But I digress. Let's get back to bridges. With weathering steel, because it is so similar to ordinary structural steel, if you follow all of the available good practice guidance on steel bridge design for weathering steel, you will end up with a good solution. That's because it has very similar mechanical properties and very similar fatigue performance as well. However, there are a couple of key design issues that you do need to think about with weathering steel due to the nature of the material. The first is the suitability of the site, and the second is the sacrificial corrosion allowance. So how do you determine whether your site is suitable for the use of weathering steel? Well, ISO 9223 contains two methods for determining the suitability of the bridge site, and this is both to determine the environmental classification. The first is the environmental data approach, where you measure three key parameters: the time of wetness, the atmospheric sulfur dioxide pollution level, and the airborne salinity level. You then go and look in a series of tables, and with those three parameters you will arrive at an overall environmental classification. The second approach is much simpler. You simply take a standard specimen of the material to the site and you keep it there, and then you measure the corrosion loss using a standard method over time. Unfortunately, both measurements need to be taken over a year to obtain representative average values. This is because corrosion rates vary with the seasons. Unfortunately, it's rarely practical or even possible to delay your design decision for 12 months while you assess the environment. So in the absence of scientific data, you have to use engineering judgment, and a good place to start is ISO 12944. This contains descriptions of typical environments appropriate to each corrosivity category, and you can see them in the table here. For example, C2 would be a typical rural atmosphere, C3 would be a typical urban atmosphere, C4 is industrial and getting close to the coast, and C5 is really aggressive. So what you need to do is look at the descriptions in ISO 12944, visit the site and see which category the site falls into. The other design issue that you need to think about is the corrosion allowance. Whilst the corrosion rate of weathering steel is very low, you can't ignore it, and you have to make some allowance for the loss of section over the design life. Guidance is available in Highways Agency document BD 701, and this table takes its data from that publication. So typically, for a mild environment, you'll be adding 1 mm per exposed face, and for a severe environment, you'll be adding 1.5 mm per exposed face. Now there are a few points to note with these figures. Firstly, if you have a weathering steel bridge over a road that is subject to de-icing salt, it is classified as severe due to this salt spray from the road below. The allowances apply to all of the elements and also to the welds, which is often overlooked. There's also no requirement to make any allowance on preloaded bolts or for the interior of sealed box girders, but the use of sealed box girders is not recommended. So that was design considerations. I'd now like to look at detailing. Once again, if you follow the wealth of good practice guidance on steel bridge detailing for a weathering steel bridge, you will end up with a good solution again. But there are one or two things to think about due to the nature of the material, and these are expansion joints, drainage, controlling the runoff, interfaces and graffiti, and I'll now cover each of those in turn. Firstly, expansion joints. These have been identified by TRL as the biggest cause of single faults on bridges made with weathering steel. So, if you can, avoid expansion joints wherever possible. Use continuous construction over intermediate piers and use integral abutments. However, if you're forced to use expansion joints, locate them away from the ends of girders and install a drainage system underneath the joint so that when it does leak, the water is captured and taken away from the steelwork. In terms of drainage of weathering steel, I've already mentioned on several occasions that the formation of the stable rust layer relies on wet and dry cycles, so you have to detail the steelwork such that it can dry out. Ensure that girders are widely spaced so there's adequate ventilation around the steelwork. Avoid any overlaps, pockets or crevices because these can attract and retain moisture through capillary action. Also avoid any moisture or water or debris traps. And the two images that you can see on this slide are examples of what not to do. Cope holes are an interesting point when it comes to detailing. On painted steel girders, it's notoriously difficult to prepare the surface and get paint on the inside radius of a cope hole, so it's generally avoided by using a close-fitting snipe, where the corner of a stiffener is ground off and then welded all around. However, this creates a corrosion trap because you have three sides and nowhere for the water to go. So you have a dilemma: which is the best solution? Well, most engineers believe that for a painted steel bridge it's much better to have a close-fitting snipe than have water passing through a cope hole where the protection system is at its most vulnerable. However, on a weathering steel bridge, you don't have to worry about preparing the surface or putting any paint on, so for a weathering steel bridge it's much better to have the cope holes that you can see on the right. They typically need to be about 50 mm. And here we have an example of a series of cope holes on stiffeners on a weathering steel bridleway bridge. Again, this is from the Chieveley project. Control of runoff is important on weathering steel bridges because as the water flows over the steelwork, it will pick up corrosion products, which in turn, if it flows over porous surfaces such as concrete abutments or piers or paving slabs, it can streak them brown and cause staining. But this problem is known about and easily avoided by providing drip details on the bottom flanges of girders, as you can see in the image on the right. So any water flowing along the bottom flange will hit the drip detail and then fall harmlessly to the floor. It's also advisable to provide generous falls on bearing shelves to the rear of the abutment bearing shelf to a drainage system to convey the water away. It's also advisable to seal substructures with a washable organic coating, such that if rust staining does occur, it can be cleaned off. So let's move on to interfaces and start with concrete. Where weathering steel and concrete are in contact with each other, it's advisable to seal the interface to prevent the ingress of moisture. Otherwise, if moisture gets into the gap between the two, it will cause accelerated corrosion due to crevice effects. So the areas that you need to seal are where the weathering steel goes into an abutment wall, as you can see on this slide here, and also on the top flange of the weathering steel girder where it's in contact with the underside of the concrete slab. So all you need to do is put a bead of sealant along those edges and the problem of concrete interfaces goes away. Remaining with the interfaces, let's now look at interfaces between weathering steel and ordinary structural steel or stainless steel. Now, where these two metals are in contact, there is a risk of bimetallic corrosion. Now, for bimetallic corrosion to occur, you need two dissimilar metals in direct electrical contact in the presence of an electrolyte. When that happens, you get an electrical cell set up and you get accelerated corrosion at the interface position. So, it's advisable to generally avoid bimetallic connections. On a weathering steel bridge, the area you need to look at is the bearings. Firstly, let's look at mild steel bearings. Now, the electrical difference between weathering steel and ordinary structural steel is very small, so there's very little driving force for bimetallic corrosion. In addition, the mild steel bearings are always painted, so there is no contact with an electrolyte. So bimetallic corrosion is not an issue for weathering steel girders on mild steel bearings. For stainless steel bearings, there is an issue in that there is a significant difference between the electrical behaviour of weathering steel and stainless steel. In addition, the stainless steel bearings are exposed to the elements, so there is contact with the electrolyte. However, the surface area of the weathering steel is so vast in comparison to the stainless steel bearing that the effect is very small. In addition, the girders and the bearings are generally sheltered, so the time that the electrolyte is present again is very small. So whilst there is a risk of bimetallic corrosion of weathering steel girders on stainless steel bearings, it is fairly small. But it can be eliminated completely by running a bead of sealant between the stainless steel bearing and the weathering steel tapered bearing plate. This seals the potential crevice and introduces a break into the electrical circuit. Interfaces with people is an interesting area. It's generally advisable to avoid contact between weathering steel and people. This is because as the stable rust layer forms, the weathering steel is friable, and as people brush past it, flakes of rust can come off on their clothes. It's also worth knowing that the texture of weathering steel is a bit like coarse sandpaper, so again there is a risk that if people brush past it, they can snag their clothing or cause abrasion damage. So this can easily be avoided by providing handrails and barriers, as you can see on this example here, which is the elevated walkway at Kew Gardens. But I'm not sure whether this is a real problem or a perceived problem, because you saw on an earlier slide the Angel of the North. Well, if you're ever lucky enough to be up in that part of the country, go and visit the Angel of the North and look at the feet. The feet are polished smooth, and the reason for that is that when people go up there and have their photographs taken, they always sit on the feet of the sculpture, and neither Tata Steel nor BCSA are aware of any complaints of rust flakes on clothing. Now let's turn to graffiti. Graffiti is a problem on any bridge, be it steel, concrete or weathering steel. It's advisable to discourage access to the bottom flanges of such bridges, and this can easily be achieved by using sloping plates as shown on the slide here. This denies the artist a foothold, shall we say. Now, the removal of graffiti depends on both the nature of the weathering steel rust layer and also the nature of the material used to put the graffiti onto the bridge. Chalk graffiti is relatively straightforward to remove, and this can be removed by low pressure water jetting, and that is unlikely to damage the stable rust layer. However, the removal of paint graffiti is much more difficult. Higher pressure water jetting is almost certainly going to be needed, which may disrupt the stable rust layer, and if the paint has really stuck well, you may have to introduce abrasives as well, in which case it will remove the stable rust layer completely back to the bare metal. Now turning our attention to fabrication and installation, starting with welded connections. As I mentioned earlier, weathering steel has a higher carbon equivalent value, and this will affect weld procedures, but any competent fabricator is quite capable of welding weathering steel. All welds should be continuous to avoid crevices. All welds on bridges are continuous anyway for fatigue reasons, so I guess that is not an additional requirement. Electrodes of matching chemical composition to that of the parent metal should be used for the capping runs of multi-run fillet welds. But for ordinary single-run fillet welds up to 8 mm, you can use ordinary electrodes. That's because there is sufficient absorption of the key alloying elements out of the parent plates into the weld pool to give you the corrosion resistance that you need. For bolted connections, all the bolts, nuts and washers need to be weathering grade material with chemical compositions that comply with ASTM A325 Type 3 Grade A. You should not really use load indicating washers on weathering steel bridges because these create crevices. On the subject of crevices, there are also rules in BD 701 to limit the bolt spacing such that you don't have the crevices and the associated accelerated crevice corrosion. In terms of surface preparation, it's advisable to specify a post-fabrication blast clean. This will assist with the uniform formation of the rust layer once all the fabrication has been carried out before it goes to site. This means that when it gets to site, all of the weathering steel will start corroding at the same point and give you a nice uniform appearance. During fabrication, it's advisable to avoid the use of paint, wax and crayon for marking the steel. This is because it's difficult to remove by blast cleaning and will adversely affect the appearance of the material in the short to medium term. In terms of installation, the steelwork contractor will take care on storing and handling the material on site. The idea is to avoid damaging the rust layer as it forms. Although it will reform over time, the damaged areas will appear different to the undamaged areas until the whole surface stabilises. It's also advisable to seal any precast permanent formwork before you put the concrete on to avoid grout runs. Whilst the grout runs themselves are not damaging to the weathering steel, again it will adversely affect the appearance of the material in the short to medium term. It's also advisable to use polythene sheeting around the substructures to minimise the risk of rust staining on the concrete piers and abutments. And this polythene should be removed just before the final inspection is made. There are cases in the UK where the outer faces of the outer girders of weathering steel bridges have been painted for aesthetic reasons. However, the aesthetic arguments are subjective, and painting the weathering steel increases the cost and future maintenance requirements of the bridge. In some cases, however, painting of the external faces is essential to permit the use of weathering steel in atmospheric environments that would otherwise preclude the use of the material, for example, the outer faces of box girders in marine environments. If painting is required, you should consider weathering steel just the same as ordinary structural steel and specify similar surface preparation and similar coatings. Moving on now to inspection and maintenance. All bridges require routine inspection, monitoring and occasional maintenance to ensure satisfactory performance. Weathering steel bridges are no different. However, it's important to identify any of the specific problems to which such bridges are occasionally prone, and this needs to be done early to allow appropriate remedial measures to be taken. Things to look for are the condition of the rust layer. A tightly adherent rust layer, such as on the top right, indicates satisfactory performance. Rust bubbles, laminations and heavy flaking indicates unsatisfactory performance. Leaking expansion joints is something else to watch out for, and it's fairly obvious if you've got one. Also look out for the accumulation of dirt and debris, overgrown vegetation around it as well, because that will create a damp environment and increase the time of wetness and lead to accelerated corrosion. It's also advisable to monitor the residual thickness using ultrasonic gauges such as the one shown in the bottom left. The remaining steel thickness should be measured at clearly identified critical points on the girders. These locations should be defined on the as-built drawings or in the bridge maintenance manual, along with the original thickness measurements taken at the end of the construction period. Plotting the thickness loss after each principal inspection allows an estimate to be made of the total predicted loss of section over the life of the structure. However, I'd suggest that you need to take at least 4 measurements to plot a reliable curve that allows for the decreasing rate of corrosion. If after say 18 years the estimated total loss exceeds the original allowance, then remedial measures may need to be taken. But don't panic, this approach should give you plenty of warning to allow any such remedial work to be carried out at a convenient time in the future. In terms of routine maintenance, weathering steel shouldn't have a great deal at all. If there's a build-up of dirt and debris on the girders, it may need to be removed by periodic cleaning. If the vegetation around the bridge grows up and creates a damp environment under the bridge, again the vegetation may need to be removed. Drainage systems should be regularly cleared, and if there's evidence of excessive corrosion around bolted joints, this is often called pack-out, then those bolted joints need to be raked out and sealed with an appropriate sealant. In the unlikely event that weathering steel bridges don't perform satisfactorily, rehabilitation is feasible. What you can do is you can blast clean to remove the rust layer and then you can repaint the steelwork. You can either repaint the whole bridge or you can just repaint the affected area. The picture shown on this slide is a typical repair following a leaking expansion joint. What's happened is that the contractor has replaced the leaking joint. They've installed a guttering system underneath the new joint, so when that leaks it won't cause the same problems, and they have blast cleaned and painted the end 1 metre or so of the main girder. Now the colour of the painting that you can see there is an undercoat. The top coat will actually be a dark brown colour to match the colour of the adjacent mature weathering steel. So in conclusion, a well-detailed weathering steel bridge in an appropriate environment can provide an attractive low maintenance and economic solution in many locations. Thank you for listening.